Hello everyone, my name is Vikrant Jain, and this is my video presentation for Lab 4 of Physics 2211. The purpose of this lab was to examine and understand the motion of a spring mass system in which the mass swings in an arc while also oscillating on the spring. We did this by applying several fundamental principles of physics to our analysis process, primarily the momentum principle, Hooke's law, Newton's second law, and the energy principle. Furthermore, as we reach the conclusion of our discussion, we shall understand how the energy principle is indeed satisfied during the lab. Our first step in this lab was to obtain position data using Tracker from the video we downloaded offline. We set our calibration stick to be 0.7 meters for the fixed attachment point up here down to the mass hanging on the spring. By setting the origin to be at the fixed attachment point, we were able to see how the object was hanging in the negative y direction. We then tracked its position as it oscillated and swung on the arc, and later saved this position data from our tracker data file to a CSV file so that it could later be employed in our code. Using the position data from Tracker, we could also then find the spring stiffness. The formula for one period is this. We found t to be 1.519 seconds for one complete oscillation through the use of Tracker, and then rearranged this formula and plugged in our value for t. And then we were able to thus find our spring stiffness to be 6.88 newtons per meter. The relaxed length could also be found using the same strategy and certain specific fundamental principles. Firstly, it was important to understand that the gravitational force and spring force are equal at static equilibrium. By understanding this, we were able to rearrange the equation and plug in the spring stiffness we found previously to calculate our relaxed length to be 0.127 meters. So, our system in this lab involved the mass, the spring, and the earth. Here we can see the initial far mass and initial velocity was 0 before Dr. Greco let it loose. Here we instruct the Python to read the CSV file that was saved from our tracker data, and the time step was then set to be 1 over 210, and the constant variables were set to be inputted as the values needed to carry out the functions. The gravity constant G was 9.8 meters per second squared. Our calculated stiffness was 6.88 and the relaxed length was 0.127. This section of the Python code was used to calculate a new length every time by simply subtracting the position of the ball minus the spring, and the variable LHAB was used to denote the direction, and the variable S was used to denote the stretch or compression of the spring, with the positive value suggesting the spring being stretched and the negative value of S being suggesting that the spring is being compressed. The next part of the code simply computed the system energies as shown. Kinetic energy is 1/2 mass times velocity squared, potential gravitational energy is mass times gravity times position y, and potential spring force is 1/2 times the stiffness of the spring times the stretch or compression squared. This was very important as we moved on to that calculation loop, where we can see the initial energies defined. We have two forces in terms of gravity and spring, and then we have the spring in terms of simply Hooke's law, negative Ks, and gravitation in terms of only the y component because the object is hanging in the negative y direction. The sum of these two forces is the F net, as shown. Here we have the momentum principle in terms of using Newton's second law and the equation for finding the final position of the mass using initial velocity and delta t. The combination of these principles was key as we found a new ball dot pause. We could find a new length every time. So with a new length every time, we could also find a new stretch or compression every time, and similarly we could find a new velocity at every position, and thus also find a new kinetic energy. So basically, this portion of the code allows us to continuously update all the information we know and simply graph it with the code below. When running the code to create a computational model for the sum of total energies, this is the resulting visual. The blue ball is the mass involved in the video, the blue arrow is the spring force, the black arrow is the gravitational force, the red dot is the position data from the tracker, and the blue dot was theoretically supposed to overlap the red dot throughout the visual, but it does not, as shown in this graph, which represents model versus experimental position data, with the red being the tracker, the blue being the model. The lack of an exact overlap was most likely caused by not choosing the exact point mass in the tracker as well. This graph represents the different energy changes, with the blue line being delta K, the red line being delta US, the green line is delta UG, and the sum of all the energies is 0, as shown by the yellow line. Because the sum of all of them is 0, which means energy is conserved, and this allows us to denote that and deduce that the Earth was included in our system. So for the first what does it mean question, the energy principle is definitely satisfied as delta E is 0 joules as the principal notes, since we can include everything in our system. So for the second question regarding juxtaposing the periods of oscillation, I found my x value to be 1.519 seconds and the y value to be a bit smaller at 1.330 seconds, as found using my tracker plots. This difference is expected as the mass is moving in a pendulum motion for the x dimension and in a harmonic spring motion for the y dimension, and this is the formula used to find the period for the pendulum motion, dealing with the length over gravity. Here's the formula to find for the spring motion dealing with mass over stiffness. So this is why they are different and are supposed to be different. In conclusion, using a combination of the principles of the momentum principle, Hooke's law, and Newton's second law, and the energy principle, we were able to analyze successfully the oscillation and motion of a spring object and demonstrate how it follows the energy principle, with delta E equaling 0.